Hello everyone, welcome to the final lab today. This is going to be a very simple lab, but you will be learning a new thing which you have not learned so far. You've been doing DC operating point analysis as well as we have done transient simulation where we look at the transient response of the system. But today we are going to do the AC simulation. All right, or you can say that it's a frequency response. This is what we are essentially looking when we are doing an AC simulation. What we, I mean, the typical example is the filters. In filters, the system responds to certain frequencies. We have certain values which are sent, certain input values which are sent to the output as it is, as long as the frequencies are within the pass band region. The moment the frequencies are in a no pass region, the filter starts attenuating those input values. So these are called these filter responses are in the form of the frequency response of the system, and to run these kind of simulations we have to use the AC simulations. So let's go to the file and new cell view. I'll say lab 6 low pass filter, not the ADXL, not the ADXL. So no, I want to open the lab 6. Did I name it now? No, not yet. Okay, so file, new cell view, lab 6 low pass filter, and I need the schematic here. Schematic, okay. All right, for simple low pass filter, it's also called an RC filter, where the input is applied to the resistor while the output is taken at the capacitor. So I'll instantiate resistor. Okay, I'll rotate it. I'll instantiate, hit the I key, bring in the capacitor, put it over here, instantiate, hit the I key, bring the ground, put it somewhere here, and then instantiate V sine, sinusoidal wave, and put it somewhere here. Hit the escape key, hit the F key, and you will fit the window. Hit the W key to wire the circuit. And you can connect it here. All right. So our circuit is done. That's a very simple circuit. We can start labeling using L key. Hit the L key, and I'll call it V in and V out. V in is here. Well, V in is not important. I'll just explain now why it's not important in this particular simulation. Let me take the resistor value 1 kilo ohm. That's okay. We'll give it default. For the capacitor value, we can say give me 1 picofarad. Even that is okay. All right. Sorry. So I'll use both default values. Perfect. And then for the AC simulation, when you're looking at the frequency response, we are just using a voltage source, such as sinusoidal voltage source. You go to the Q, and then you just set the AC magnitude to be 1. Please don't use the amplitude from here, because you are doing the over here, because you are doing the AC simulation. In AC simulation, as I said, you are looking at the frequency response. What does that mean? That your AC will have a small signal magnitude of 1 volt, and you will be sweeping the frequency. In the AC simulation, will be defining that the system will show us the response to different varying frequencies. All right. So I've used AC magnitude. This is very important. AC magnitude to be 1 volt. Perfect. Okay. All values are default. Let's go check and save. Perfect. Launch ADXL. Create new view. Yes, that one. Hit the test. Yes, low pass filter, setup, environment. Very important to set the environment to 64-bit. And then go to the AC simulation here. We'll select from transient. We have done transient, we have done DC. Today we are going to do AC simulation. Sweep the variable. Which one is the frequency? Start frequency is 1 Hertz and stop frequency is 10 megahertz. I just chose. So system is going to sweep the RNC to the RNC response to all the varying frequencies. Or I'll say OK, and then select the output from design. I'll just look at the output because the input, as I said, is a 1 volt magnitude and nothing else. I'll choose VN just to show you guys what do I mean by that. You go in here, ADXL, VNV output is selected, and then we can run the simulation. Okay, so plots are generated, new window, plot all here. So that blue line is the input value. It was 1 magnitude and it stays as 1, so that's not important. But yes, for these values, we can see the filter response as this. Let me keep the same filter as it was. All right. Now, as we know, that the filter response, the cutoff frequency of a filter, of a low pass filter, is also for the high pass filter, is when the output voltage becomes 0.7 volt. All right. So when the output voltage is 0.707 volt or 707 millivolts, then we can say that the cutoff frequency has been reached. Right now, all this magnitude is too big because our values are too small. Let me quickly change one of the values, and I'll show you the beauty of what we are going to do today. You will see that I'm changing the value to 1 nanofarad now. You see, I have to come back and change the value. I'll go check and save, go to ADXL. I'll run the simulation again. Plot the plots. Okay. I don't want to see the input. As I said, 0.707. So here 0.707 is somewhere here. Okay. So when you reach that value, hit the M key. When you hit the M key, it will make a marker over here. You see, and then these values are visible, all right? So it is telling me that at 706, approximately 706, the cutoff frequency is 158.89 or 159 kilohertz. That's the cutoff frequency when we have R to be the 1 kilo ohm, and when C value is 1 nanofarad, as I've said, the frequency is cutoff frequency is 159 kilohertz. All right, that's the marker. You can set the marker properties by clicking the marker and hit the Q key. And if you don't want to see the M1, which actually I don't like, personally, because in your assignment you might have to remove that if you think it's necessary. And I'll tell you later why I'm saying that. I'll say OK, and you see M1 is removed and I can only see the voltage and the cutoff frequency. All right, now if I want to see that how does the system respond to a different another value, for example, then all I have to do is to go and change C value again, and then this cycle will continue. Instead of that, today we are learning the parametric sweep. In parametric sweep, I want to cycle the values of C from 1 nano to 10 nano to 100 nano, different values, and I want to see with by keeping the R values same, how does my system response. So I'll hit the Q key, and instead of the value, I'll call it cval or any other name, value of cval underscore c, whatever. So cval means I have given it a parameter. I've given a name of a variable, and I'll say hit check and save. Now I'll go to ADXL. In ADXL, now I have to go to the test and the open test editor. All right. In test editor is already open here, ADXL test editor. Now, what I want to do is this. I'll go to this second tab over here, which is edit variables. As you see, there is nothing right now. There are no design variables, but actually cval is my design variable. So I'll say select the variable copy from design. All right, copy cell view variables, copy from, and you see the cval is appearing here. All right, so now cval has appeared. You name it, you click it, and it will be named here. And now I'll say that I want this variable to have 1 nano, 10 nano, and 100 nano, these three values. All right, and then I'll hit apply and OK, and you see these three values appear here. For the outputs, we have already chosen the VN and Vout. I'll just deselect the VN. All right, so once this is done, now I'm telling system that keeping my R value to be 1 kilo ohm, keep it same, and just cycle 3 different values of capacitor, which are now visible in the global variables here. And let me see how my plots look like. So I'll hit the simulation key now, and you see 3 plots are being made now. First one done, second, all plots done. Hit the plot all button, and you will see here, here, all 3 different plots have appeared. Now if you, let me just move a little bit over here. If you hit this plus key, there's a small plus key, and it will show you all different plots. So it has the red one is the one when the capacitance value is 1 nano, and then the yellow one is 10 nano, and C when it's 100 nano. So we said that for the 1 nano, we already know 159 kilohertz was the value, right? So 707. Okay, somewhere here. Okay, hit the M key, and that's the marker. And then for this one, what is the value? 707. It is hit the M key again, another marker. Hit the 692. Okay, hit the M key, and these are the 3 markers. In your lab assignment, you will be plotting 9 different plots, and then you might have these markers overlapping each other. Just in that case, to make sure that they're not overlapping, you can hit the Q key and just remove these %M sign, or and then apply and OK, and then you will see that the markers are removed, the number of markers are removed. All right, here you can observe that the red out is when the frequency, when the capacitance value is 9 nanofarad. For your lab assignment, when you're doing it, you can attach all the plots, and then one more plot showing exclusively these marker values. You can just zoom them so that they are not overlapping each other. This is very important, that they should not be overlapping, and I want to see these marker values and the cutoff frequencies for the plots and their colors specifically visible. Now we have done that, but let's say we want to go and we want to change even R values. So I want to see not just 1 kilo ohm, and I want more values of R. So I'll say I'll say RVal as another variable. Hit check and save. I mean, you now know the procedure actually. and then I'll go to the test editor again, hit the open test editor, then again the second tab from design, copy from design. Yes, these R values, you click R values, and then 500 ohms, and then 2 kilo ohms, and then 5 kilo ohms, just random values. For your work I have actually supplied these values. All right, I'll do OK. You see our values are appearing here, and then output we already know. Let's simulate the and you will see the global variables are variables now appear. Now in the end you will be able to see 9 different plots. So the system will keep 500 ohm and will sweep it to 1 nano, 10 nano, 100 nano, and the next instant it will take the 2k value and will cycle through all 3 plots, and similarly 5k value and cycle through all the plots. Let's simulate. You should see 9 plots now. All right, all done, all the plots. Here are your 9 plots. You can hit that plus key and you will be able to see all the combinations. So red is 1 nano. I can just turn off all of them. So just red 1 nano and 500 ohm. This is the plot, and its cutoff frequency is somewhere here. Hit the M key here. So that's its cutoff frequency. Similarly, yellow one is when 1 nano and 2 kilo ohm is the cutoff frequency, is the RC value, sorry. And then this is their cutoff frequency. Or you see that, I mean, they've already started overlapping. That was the thing I was saying about. So for this one, actually, it will be overlapping. It'll start overlapping more. So in that case, when all those 9 plots are visible, you can just take one picture, I mean attach one screenshot, high definition screenshot, another one by showing these plots. Still, if they're overlapping, all you have to do, as I said, is to select the queue and just remove that part, and then OK. And similarly this one. All right, you can even zoom more to get the values. But I mean, if I can see that these are the 3 plots, then I should be able to see their values here. So please don't forget to hit the plus button. All these instructions, very simple. Lab is the last lab, so I just don't want you guys to do more things. You can prepare for your exams for the lab. I just want you to do the same thing for the high pass filter. For the R values, you have to sweep these 3 values. For the capacitors, these 3 values, and then screenshots of the cutoff frequencies. When please note that use markers in the plots, and I'm asking you to that the plots are not overlapping and the cutoff frequencies of plots are clearly visible. Okay, the markers of adjacent plots should not be overlapping. And again, as I said, you can zoom the marker areas to ensure there's no overlap. So very clear instructions on what to do. Just a simple passive high pass filter. That's all you have to do. I hope everything is clear. If there's any question, I hope there will be not, because it's too simple and you guys have done quite difficult labs already. And yeah, this is what we can do, and this is called the parametric sweep. This is very useful when you have to look at the system response against a frequency, when you're designing some system and you want to exactly know that what are my limitation, how my system responds to what frequencies, and instead of changing values each and every time, like I've done in the beginning, like changing capacitor value from 1 pico to 1 nano, you can set the range of values. Actually, right now I've given it a list, but in Cadence, as I've explained earlier in some labs, you can use the system of defining the values. Like you can give it an initial and final value, and then let the system do the sweep itself. For example, this is just one way. I'll say add specification. I'll say from and to. All right. So when I say from and to, I can give it a step value that from this value to this value, and how many steps do you want? Like for example, I want from 1 kilo ohm to 10 kilo ohm, give me 10 steps. So it will do 1 kilo, 2 kilo, 3 kilo ohm steps automatically. That's also one way of defining. You guys should know each and everything. That's all from my side. I hope everyone can do this lab quickly and submit it. And good luck for your final exams. Have a good day.